Welcome to this next lecture on acoustics. So we have found the separable solutions for the wave equation in spherical coordinates. Okay. So before I go ahead and give you the full solution, let us look at some of these functions. Okay. So for example, we have come up with Pmn of cos theta. Okay. So and we have also come up with Jn's and Yn and Hn of 1 and Hn of 2. Okay. And of course e to the power plus minus Im phi. So now let's look at Pmn of cos theta or the Pmn functions. Okay. Now if m is 0, okay, so now theta goes from 0 to pi, then cos theta is of course lies at between minus 1 and 1. Okay. So if we consider Pmn of x such that x is between plus 1 and minus 1. Okay. So we are looking at Pmn of x. If m is equal to 0, first of all, if m is 0, then we have P0 of n of x, which is equal to Pn of x, which are the, let me call them the regular Legendre polynomials. Okay. And how do they look like? They look like, for example, P0 of x is 1. Okay. Then P1 of x is x. P2 of x is equal to half 3x square minus 1. Okay. And P3 of x is 1/2 5x cube minus 3x. P4 of x is equal to 1/8 35x fourth minus 30x square plus 3, and P5 of x is 1/8 63x 5 minus 70x cube plus 15x. Okay. A simple formula to get this, okay, is Pn of x is 1/2 to the power n n factorial dn by dxn x square minus 1 to the power n. Okay. They have an orthogonality relation, which is given by integral from minus 1 to 1 Pn of x Pm of x dx is equal to 2 over 2n plus 1 delta nm. This is important. So we'll store it in the blue color. Okay, so save this in some place. Okay. Now we will also, just for the sake of information, keep this. Now what are PMNs of x when m is not equal to 0? So they are Pmn of x is minus 1 to the power m 1 minus x square m by 2 dm by dxm of Pn of x. Okay. So these are derivatives of the regular polynomials. This is a regular Legendre polynomial. Okay, this is a regular, what I have written here is the regular commonly known Legendre polynomial. They are very well behaved polynomials. Okay, if you want to do numerics, they are very good, and their orthogonality relation is very simple. Okay, so now, so m, when you have an m over here, it's the mth derivative of the regular polynomial. So what happens if I take, if this is 0, or let us say if this is 1, okay, P1 of x is x. So I take one derivative and it's a constant, okay, 1, it becomes 1. Second derivative, it goes to 0. Okay. So if the subscript is 1, I can take only one derivative. Similarly, Pn, if n equal to 2 here, I take one derivative, I get 6x. I take another derivative, I get something else. It's a constant. But if I take the third derivative, this goes to 0. Okay. Similarly, P5 I can differentiate 5 times. So n, if there is an n, m can go only up till n. The limit of m is n. This is important to remember. Okay. So because in the final summation, this limit will, we have to sum the m also, and so m will sum from minus n to plus n. Okay. Now let us see a few more. Okay. So we will see this Pn of cos theta, okay, as a function of theta. Okay. So if n is 0, we have p0 cos theta, and theta goes from 0 to pi. Okay, so this fellow is a constant. Okay, this fellow is a constant. How does he look? He looks like a constant. Okay, 0 theta, 0 to pi. So constant value 1. Okay, this is n equal to 0. If I now have n equal to 1, okay, it is x, that means x is cos theta, right? So if x is cos theta, how will it look like? At theta equal to 0, it is plus 1, and theta equal to pi, it's minus 1. At theta equal to pi by 2, it goes through 0. This is how it is. So this is minus 1, this is plus 1, this is 0, and this is theta. This is theta at pi by 2. Okay. Next is if I have n equal to 2. N equal to 2. N equal to 2 is cos square theta, 3 cos square theta minus 1. Okay, so that will look like at theta equal to 0, we have 3 minus 1, 2. 2 divided by 2 is 1. Okay, and then in between it will go through a couple of zeros. It will come back up and go back to 1 at theta equal to pi. Okay. Now if I have n equal to 3, then it will have start off at 1, come back to a 0, another 0, another 0, and it will go back to minus 1. And so forth. Okay, so in between oscillations have lower amplitude, but it ends up at the end points as plus minus 1. Okay, so now two more relations that we will need, and we'll collect them later. Okay, one is that p negative m n of x is equal to minus 1 to the power of m n minus m factorial divided by n plus m factorial p m n of x. Okay, and then we had given the Legendre polynomial orthogonality. What is the p m n function orthogonality? Okay, that is given by, let me write it here, integral going from minus 1 to 1 p m n dash of x p m n of x dx is equal to twice over twice n plus 1 n plus m factorial by n minus m factorial delta n dash n. Okay. I should mention, probably I am taking this from the book Fourier Acoustics. I had mentioned this earlier, Fourier Acoustics by the author Earl G. Williams. I am taking it from there. Okay. So now this is also important. This is important. So let me gather it. We will gather all of them together later. This is another important orthogonality relation. Okay. Now just to give you a feel for the p's, so if I p m n, okay, of now cos theta, okay, if m is 0 and n is 0, we saw that it's 1, p 0 0 is equal to 1. Okay. Now if m is 0 and n is 1, it was x over there, so here it is p 0 1 is cos theta. Okay. If m is 0 and n is equal to 2, it was 3x square minus 1 by 2. So this is going to be looking like, after simplification, 1 plus 3 cos 2 theta upon 4. Okay, this value over here. Okay. Similarly, if we look at m equal to 1, okay, and then n equal to 1, so what will it be? It will look this function p 1 1 looks like minus sine theta. Okay. So if m is equal to 1 and n equal to 2, then we have p 1 2 looking like minus 3 cos theta sine theta. Okay, this can be derived from here. This can be derived from here. I'm sorry, it can be derived from here. Okay, not here, here. Okay, and if m is still 1 and n equal to 3, and this p 1 3 as the look 3 times 1 minus 5 cos square theta sine theta by 2, and so forth. Okay. Now let's just see some more. If m equal to minus 1, okay, m equal to minus 1 and n equal to 1, then p minus 1 1 is equal to sine theta by 2. Then if next is, let me do this. Then P minus 1 is equal to sine theta by 2. Okay. If m equal to minus 1 and n equal to 2, then I have P minus 1 2, that looks like cos theta sine theta by 2. Okay. So the form remaining the same, the interior form is remaining the same, the constant in front is changed. Similarly, the form is the same, the constant has changed from minus 1 to half. Okay. So let's look at the last one. If m is equal to minus 1 and n equal to 3, okay, then I have P of minus 1 3 given by 3 plus 5 cos 2 theta. Cos 2 theta is in terms of cos square theta, right, into sine theta divided by 16. Okay. So again this form remains the same, the constants change. Okay. So that's how the Legendre functions they move. There are a lot more relations, but we don't need all of them. Okay. Now the next is here is what we are going to do is combine these Legendre polynomials and associated Legendre polynomials, and the e to the power I m phi function. So essentially the Legendre polynomials are looking at the theta direction and the I m phi is looking at the phi direction. Okay. So we have r theta phi, three directions. The Legendre polynomials and associated Legendre polynomials are looking at the theta direction, whereas this e to the power I m phi is looking at the phi direction. So we combine the two. We combine the two functions and we add constants, we supply constants so that the orthogonality remains for orthogonality. Okay. So now the function that combines the theta Legendre polynomials and phi, this exponent, is called the spherical harmonic. It's called a spherical harmonic. Because the r is not there, it's supposed to be at a constant distance independent of r. Okay. And therefore this is a spherical harmonic. It is given a symbol y mn theta comma phi, which is equal to, now we supply these constants, twice n plus 1 by 4 n minus m factorial by n plus m factorial Pmn cos theta e to the power of I m phi. Okay. So this is a Legendre, this is a spherical harmonic. Okay. So now we will have the chance for a negative index also. So how are they related? Y minus mn of theta comma phi is equal to minus 1 to the power m y mn theta comma phi. Okay. Let's see over here. The I'm sorry, one second. There is a conjugate. Okay. So now what is the orthogonality? The spherical harmonic orthogonality. Okay, that's given by integral 0 to 2 pi d of phi integral 0 to pi y m n theta comma phi y m dash n dash theta theta comma phi conjugate sin theta d theta is equal to delta over n n dash and a delta over m m dash. Okay, so let's see this how it works. We have let me just recall, I keep forgetting. Let me take this here. So now if I have if I try to do this, I have integral 0 to 2 pi d phi integral 0 to pi y mn is square root twice n plus 1 by 4 n minus m factorial by n plus m factorial p m n of cos theta e to the power I m phi. Okay, that's y m n theta, and y m dash n dash conjugate. Okay, so these are real functions, so conjugacy comes only here. So what is y m dash n dash? It is square root of twice n dash plus 1 by 4 n dash minus m dash n dash plus m dash, and then p m dash n dash cos theta e to the power of minus I m dash phi into sin theta d theta. So now if we do the phi d theta, d phi is already there. Okay, so if I do the phi integral first, okay, then so I have phi integral doing what? I have integral 0 to twice pi e to the power of I phi m minus m dash d phi. Okay, so what is this equal to? If m is not equal to m dash, this is equal to 1 by I m minus m dash e to the power of I phi m minus m dash over 0 to 2 pi. Okay. So m and m dash are both integers, so difference is an integer. So evaluated at phi equal to 2 pi and 0, it is 0, so this is 0. Okay. And if m dash equal to m is equal to m dash, then this is a 0 over here, so this is 1, so I have 2 pi and I get 2 pi. Okay. So let us say we have done the m or the phi integral. So we are now left with integral 0 to pi, and m has to be equal to m dash. So I have square root, or let us say I have p m n cos theta p m n dash cos theta sin theta and some constants. Okay. So product of this and this is a huge constant, so I am going to keep it there. So and d theta. Okay. So if I set cos theta is equal to x, then minus sin theta d theta is equal to dx. Okay. When theta is 0, x equal to 1. When theta is equal to pi, x equal to minus 1. So I have integral 1 to minus 1 p m n of x p m n dash of x, and sin theta d theta is minus dx, and these constants. Okay. So if we now look at the orthogonality, okay, p m n dash p m n dx is this entity. So let me take it with me. So I have, so this is what it is. So what I will do is, we are out of time, so I will stop this lecture over here, and we will continue this in the next class. Thank you.